Hi everyone, it's Professor Pemberton, and today we're going to talk about triple integrals in cylindrical coordinates. So earlier, we showed how to convert a double integral within rectangular coordinates into a double integral using polar coordinates to deal conveniently with problems involving circular symmetry. A similar situation occurs when you have triple integrals with cylindrical coordinates or spherical coordinates, where you want to use cylindrical symmetry or spherical symmetry. In this section, we're going to convert triple integrals in rectangular coordinates involving variables x, y, and z into a triple integral either in cylindrical coordinates using z, r, and theta, or spherical coordinates which involve rho, theta, and phi. So in this video, we're going to talk about how to evaluate a triple integral by changing from rectangular coordinates to cylindrical coordinates. Let's review a little bit about cylindrical coordinates. We've seen earlier that if you have the two-dimensional case, if you have a point in rectangular coordinates, x, y, and you want to identify what is the equivalent point using polar coordinates, which is r, theta, then you have the equations x equals r times cosine theta, y is equal to r times sine theta, and then x squared plus y squared is equal to r squared. In three-dimensional space, a point with rectangular coordinates x, y, z, you can identify what is the equivalent cylindrical coordinate as r, theta, z. We can use these same conversion relationships for x and y, and also x squared plus y squared is r squared, and then just letting z be representing the vertical distance to the point from the xy plane. So remember, if you want to convert from rectangular coordinates to cylindrical coordinates, you use these formulas. X is equal to r times cosine theta, y is equal to r times sine theta, and you let the z coordinate just stay the z coordinate. And then you also have x squared plus y squared converts to r squared. That represents the distance to the point x, y, where you're letting r be the distance between the origin 0, 0 and the point x, y. So remember, in cylindrical coordinates, you have the xy plane, which is where z equals 0. The cylindrical coordinates are exactly the same as polar coordinates in the xy plane. So you project this point P, which is r, theta, z, you project the point into the xy plane. You'll have this point, which is the projection of this point P, where the z value is 0. You replace x with r times cosine theta, and the y coordinate is replaced with r times sine theta. So it's exactly the same in polar coordinates when you have the point projected into the xy plane. And then you'll just let the z coordinate just stay the z coordinate to get cylindrical coordinates for the point P. We saw with triple integrals, if you have a type 1 region where you have the projection of a solid E into the xy plane, the projection will be called D. It'll be a region in the xy plane, and sometimes this region could be more conveniently described using polar coordinates. So in particular, if you have a function that's continuous, then the solid E that you're integrating over will be consisting of a point x, y, z in three-dimensional space. The x, y will be in the region in the xy plane, but then the z values are between two surfaces. The z values are no larger than an upper surface, u sub 2, x, y, and the z values will always be larger than the lower surface, u sub 1, x, y. If you have this description for the region D in terms of x and y, well, that's rectangular coordinates in the xy plane. You can convert this region D using polar coordinates as follows. The region D can be described using r and theta instead of x and y, where theta ranges between two angles, alpha and beta, and then r ranges between two curves, an outer curve, which is a function of theta, h sub 2 of theta, and r will always be greater than a function of theta, h sub 1. This will describe a polar region in the xy plane. So the situation is this: we're integrating over this solid E. We're going to project the solid E into the xy plane, and so we're going to have this general region D. But instead of using rectangular coordinates to integrate over the region D, using variables x and y, we're going to use variables r and theta with polar coordinates, because perhaps this region D after the projection into the xy plane, maybe this region D after the projection into the xy plane, it could be more conveniently described using polar coordinates. So you have a triple integral over the solid E, a function of three variables, f of x, y, z, and you integrate with respect to volume, or v. The outside double integral will be over this region D, where we're integrating with respect to z first for the inside integral. The z values will be between an upper surface, it'll be u sub 2 of x, y, and then the z values will be always greater than a lower surface, z equals u sub 1, x, y. And then the integrand stays the same. We're integrating with respect to z first because we're projecting the solid into the xy plane, and so the limits of integration for the z values will be functions of x and y. And then you have the double integral where you have integration over the region D, and that's with respect to A, or area. However, if you recognize that the region D is more conveniently integrated using polar coordinates, then you can convert the double integral on the outside using polar coordinate conversion. So the triple integral over the solid E for the integrand f of x, y, z with respect to volume, or v, it's going to be a triple iterated integral where the outside integral will correspond to values for theta. Theta will be between alpha and beta. So the smallest that theta can be for the region is alpha, and then the largest that theta can be for the region is beta. The middle integral will correspond to values for r. So remember that r represents the outer curve, and then r also represents the inner curve, the upper limit and the lower limit of integration for this middle integral. It's r equals h sub 2 of theta, that's the outer curve in terms of polar coordinates, and then the h sub 1 of theta is the inner curve. And then, instead of u sub 2 x comma y is your upper surface and u sub 1 x comma y is your lower surface for the z values, now you're converting to cylindrical coordinates. So the x becomes r cosine theta and the y becomes r sine theta. The integrand f x comma y comma z will also have to be changed in terms of cylindrical coordinates. So the x will become r cosine theta, the y will become r sine theta, and then remember the z will just stay z with cylindrical coordinates. And then remember, whenever you convert to polar coordinates, you pick up an extra factor of r multiplied by the integrand, the Jacobian, after you convert to cylindrical coordinates. And then you'll integrate with respect to z first, that will correspond to surfaces. You'll integrate with respect to r next, because that corresponds to curves, an outer curve and an inner curve for your region D. And then you'll integrate with respect to theta last, between alpha and beta, two angles. So the definition for a triple integral in cylindrical coordinates, if you have a function f, x, y, z, it's continuous over the solid that you're integrating over, E, then you can convert the triple integral from rectangular to cylindrical coordinates by writing x is equal to r times cosine theta, y is equal to r times sine theta, and then z is equal to z. You also have to change the limits of integration to be in terms of z, r, and theta. You'll have to also replace dv, the differential dv, to be r dz dr d theta, where you also pick up the factor of r when you change to cylindrical coordinates. And so this r dz dr d theta, that's what's called the volume element for cylindrical coordinates. The dv is r dz dr d theta. So note, it's worthwhile to use the differential dv, which is equal to r dz dr d theta, whenever the solid E can be more easily described using cylindrical coordinates, or whenever you have an integrand, f of x, y, z, which contains the expression x squared plus y squared. So as we've seen in the previous section, any property that we have with double integrals also works with triple integrals, whether we're using rectangular coordinates or cylindrical coordinates. Example 1, integrating over a solid using cylindrical coordinates. Evaluate the triple integral. The outside integral corresponds to x values from x equals -2 to x equals +2. The middle integral corresponds to y values. The y equals square root 4 minus x squared is the upper curve, or the upper limit of integration. The lower limit is y equals negative square root 4 minus x squared. That corresponds to the lower curve, or the lower limit of integration. The inside integral corresponds to surfaces, and that's z values. The upper surface is z equals 2, and the lower surface will be z equals square root x squared plus y squared. And then the integrand is x squared plus y squared. We're going to evaluate this triple integral by converting this integral involving rectangular coordinates to an equivalent integral using cylindrical coordinates. Since we're integrating with respect to z first, we're projecting the solid that we're integrating over into the xy plane. So we're integrating between the surfaces z equals 2, which is a plane, and then also z equals square root x squared plus y squared, that's a cone with vertex at the origin, 0, 0, 0. We're integrating over the solid that's below the plane z equals 2 and above the cone z equals square root x squared plus y squared. We're projecting this solid into the xy plane, and notice that the region that you obtain in the xy plane will be a circular region, which means that we should use cylindrical coordinates to integrate instead of using rectangular coordinates. So the region E starts with rectangular coordinates x, y, z for any point in this solid. The x values are between -2 and 2. The y values are between a lower curve and an upper curve, negative square root 4 minus x squared and positive square root 4 minus x squared. And then the z values are between two surfaces, z equals 2, the plane, and z equals square root x squared plus y squared, which was the cone. In cylindrical coordinates, this same solid that we're integrating over can be described using r, theta, and z. It'll be the same points in the solid, r, theta, z, where r values will go between 0 and 2 because the radius will be no larger than 2 and no smaller than 0 for the region after the projection into the xy plane. Theta will go between 0 and 2 pi to generate the entire region. And then z will go between z equals 2, which is still the plane, but then you have to convert from rectangular coordinates for the cone, z equals square root x squared plus y squared. Well, if you square both sides of the equation, then you'll have z squared is equal to x squared plus y squared. Well, x squared plus y squared is r squared. So this becomes z squared equals r squared, or simply r equals z. So the lower surface was the cone. That becomes, with cylindrical coordinates, the equation z equals r. So now we're ready to convert this into a triple integral using cylindrical coordinates. So the original integral is given. We're going to convert to cylindrical coordinates. The outside integral will correspond to values for theta, so theta will go between 0 and 2 pi. The middle integral will correspond to values for r goes between 0 and 2. The inside integral corresponds to the z values. The upper surface was z equals 2, the lower surface is z equals r. The integrand was x squared plus y squared, well that becomes r squared using cylindrical coordinates. And then also remember that you pick up the extra factor of r, which is the Jacobian when you convert to cylindrical coordinates. So the integrand becomes r cubed, and so you integrate with respect to z first. The antiderivative is r cubed times z. Evaluate the antiderivative at the z values, z equals 2 for the upper limit and z equals r for the lower limit. When you do this, you'll have r cubed times the quantity 2 subtract r, distribute through the parentheses so you can integrate each term separately. So you'll have 2r cubed subtract r to the fourth is the integrand. Integrate with respect to r, you'll have the antiderivative 1/2 r to the fourth for the first term minus 1/5 r to the fifth for the second term. Evaluate the antiderivative at the values r equals 2 for the upper limit and r equals 0 for the lower limit. Keep the outside integral between 0 and 2 pi. Those are for values for theta after you integrate with respect to theta. Substitute in the upper limit of integration first in for r, so you'll have 1/2 times 2 to the fourth minus 1/5 times 2 to the fifth. And then when you substitute in r equals 0, both terms will just be 0. So if you simplify, the first term will give you 8, and then the second term will give you 32 divided by 5. So the integrand is 8 subtract 32 fifths, and you have an integral from 0 to 2 pi, and you have to still integrate with respect to theta. Well, 8 subtract 32 fifths will simplify to be 8 fifths, and now you integrate with respect to theta, it'll be 8 fifths theta. And now evaluate this antiderivative at theta equals 2 pi, the upper limit, and theta equals 0, the lower limit. This will give you 8 fifths times 2 pi, which is 16 pi divided by 5. So that would be the value of the triple integral that we started with involving rectangular coordinates, which is also equivalent to the triple integral involving cylindrical coordinates. Example 2, setting up a triple integral using cylindrical coordinates. This time we're going to set up the triple integral but not evaluate. Let E be the region bounded below by the cone, z equals square root x squared plus y squared, and bounded above by the elliptical paraboloid, z equals 2 subtract x squared subtract y squared. So the graph is given just to illustrate what we're actually integrating over. We're going to set up a triple integral using cylindrical coordinates to find the volume of the region using the following two different orders of integration, but we're not going to evaluate the cylindrical integrals afterwards. So number one, the order of integration that we want is dz, dr, d theta. So we want to set up a triple integral involving cylindrical coordinates. We're going to project the solid E into the xy plane because we're integrating with respect to z first. Now we have to convert these two different surfaces in terms of cylindrical coordinates rather than rectangular coordinates. So we did the last problem, z equals square root x squared plus y squared. For the cone, that becomes z squared equals x squared plus y squared, or z squared equals r squared, and so the cone is just simply z equals r, using cylindrical coordinates. Whereas the elliptical paraboloid, z equals 2 minus x squared minus y squared, notice that you can group the x squared and the y squared terms together, and you can factor out a negative. So z equals 2 subtract the quantity x squared plus y squared. That becomes z equals 2 subtract r squared in terms of cylindrical coordinates for the elliptical paraboloid. The thing that we need to do is project this solid into the xy plane. So if you project the solid that we're integrating over into the xy plane, we need to know where the elliptical paraboloid and the cone intersect one another. We have z equals r that represents the cone, and z equals 2 subtract r squared represents the elliptical paraboloid. If you set these two equations equal to each other, you'll have r equals 2 subtract r squared. Move all terms to one side of the equation so the equation is equal to 0. You'll have r squared plus r subtract 2 equals 0, and then after you factor, it'll be r plus 2 times the quantity r subtract 1 is equal to 0. That gives you r equals negative 2 or r equals 1. Well, r cannot be negative 2 in terms of cylindrical coordinates, so r must be equal to 1. Well, since r is also the z value for the cone, that gives you a value of z equals 1. The two surfaces will intersect at the value z equals 1. So whenever z equals 1, notice that the solid that you're integrating over will project into the xy plane, and that will give you a circle of radius 1 centered at the origin. So the region for the double integral on the outside will become an integral that represents integrating over this region, this general region D. It makes more sense to use polar coordinates because you're integrating over a circular region. It's a radius 1 circle centered at the origin. So x squared plus y squared equals 1 is the equation of the unit circle, or that's the same thing as r squared equals 1 or r equals 1 using polar coordinates. So we're ready to set up the triple integral in cylindrical coordinates that represents the volume of the region we're integrating over. We want the order dz, dr, d theta. We'll have the volume equal to a iterated triple integral The outside integral corresponds to values for theta. We want theta to go between 0 and 2 pi to generate the entire region D that's in the xy plane. We want the r values to go between 0 and 1 because r equals 1 is the upper curve, which represents the circle of radius 1. And then r equals 0 is the smallest value for r. That's if you're at the origin. And then the inside integral corresponds to the z values. The z values were representing surfaces. Upper surface was the elliptical paraboloid because the region was bounded above by the elliptical paraboloid, so the upper limit of integration is 2 subtract r squared. And then the region, E, was bounded below by the cone, so the lower limit of integration, the lower surface, is z equals r. Remember, when you integrate with respect to cylindrical coordinates, you also pick up this extra factor of r, so the dv becomes r dz dr d theta. So let's try a similar problem, number 2. This time we want the integration order to be dr dz d theta. Since we're integrating using cylindrical coordinates, it makes sense to change all the surfaces to be in terms of cylindrical coordinates. So we had the elliptical paraboloid. We know that was z equals 2 minus r squared. We also had the cone, which we knew was z equals r. Since we're integrating with respect to r first this time, we need the surfaces to be in terms of r equals a function of z or theta. So if you have z equals 2 subtract r squared, if you solve this equation for r is equal to square root 2 minus z. Then the cone, z equals r is okay. It's just r equals z. Notice that the z values are between 0 and 1 for the region that we're integrating over, and then the r values are between 0 and z. And then also, if the z values are between 1 and 2, that means the values for r are between 0 and the square root of 2 subtract z. Since the r values are between two different surfaces, you have values for r equals 0 and r equals z. That's between z values between 0 and 1. And then you also have r values between square root 2 subtract z is equal to r, and then r equals 0. For the values for z equals 1 to 2, you have to separate this out into two separate triple integrals. So the volume will be equal to one triple integral where you have dr, dz, d theta. The inside integral corresponds to r values this time. So r is between 0 and z for one integral. The middle integral corresponds to z values. Well, the z values for that region is between 0 and 1. And then theta is the outside integral that's between 0 and 2 pi. Plus, then you have a separate triple integral because you have the r values also go between two different surfaces. You have the upper surface for r could be square root 2 subtract z for r, and then the lower surface could be r equals 0. Well, that corresponds to z values between 1 and 2. So the inside integral are for the r values. The middle integral will correspond to the z values between z equals 1 and z equals 2. And then again, theta goes between 0 and 2 pi. So the sum of these two triple integrals will give you the same value that we had in problem number 1, with one triple integral using cylindrical coordinates. Well, 3, we're going to set up a triple integral using cylindrical coordinates again. This time, let E be the region bounded below by the xy plane. It's bounded above by the sphere x squared plus y squared plus z squared equals 4, so a sphere of radius 2 centered at the origin, 0, 0, 0. And it's also bounded on the sides by the cylinder x squared plus y squared equals 1. The region that we're integrating over is above the xy plane. It's bounded above by the sphere of radius 2 centered at the origin, but then also bounded by the sides of the cylinder x squared plus y squared equals 1. So a cylinder that's centered along the z-axis with a radius 1. I'm going to set up a triple integral using cylindrical coordinates to find the volume of the region using, again, two different orders of integration, but we're not going to evaluate the cylindrical integrals. So number 1, we're going to have the order of integration dz, dr, d theta. Since we're integrating with respect to z first, we're projecting the solid that we're integrating over into the xy plane, which is formed between the sphere and the cylinder. Let's convert the equation of the sphere into cylindrical coordinates, and also the cylinder in terms of cylindrical coordinates from rectangular coordinates. The equation of the sphere in rectangular coordinates was x squared plus y squared plus z squared is equal to 4. Well, x squared plus y squared in cylindrical coordinates is just equal to r squared. So this is the same equation as r squared plus z squared equals 4. That represents a sphere in cylindrical coordinates. And then a cylinder using cylindrical coordinates is pretty easy. X squared plus y squared is equal to 1 was a cylinder. X squared plus y squared is equal to r squared again. So you have r squared equals 1, or that gives you r equals 1. So r equals 1 is a cylinder centered along the z-axis with radius 1. So since we're projecting into the xy plane, because we're integrating with respect to z first, let's find out what the region that we're integrating over after the projection into the xy plane. So the region is bounded by the cylinder, the sides of the cylinder. It's bounded above by the sphere and above the xy plane. If you project that solid into the xy plane, you'll have this region. So we're ready to set up our triple integral now. The volume that we're trying to find can be represented using an iterated triple integral, where we're integrating with respect to z first. That'll be the inside integral. r will be the middle integral, and then theta will be the outside integral. Well, notice for this region that we're integrating over, theta ranges between 0 and 2 pi, so that's your outside integral. Your middle integral are r values, which are between r equals 0 and r equals 1. And then your surfaces, your upper surface was the sphere. Well, you only want the upper half of the sphere, the upper hemisphere. That will give you the equation z equals, if you solve this equation for the sphere for z, you'll have z equals positive square root 4 subtract r squared. And then the lower surface was the xy plane, that's z equals 0. And remember, when you integrate with respect to cylindrical coordinates, you pick up this extra factor of r in the integrand. So it will be integrand r, and you integrate with respect to z first for surfaces, then you'll integrate with respect to r second, that will be representing curves, and then theta will be on the outside that represents numerical values or angles. Let's try one more. Number 2, you want to integrate with respect to r first, then z, and then theta last. So again, we're going to integrate using cylindrical coordinates, but in this order. We want to integrate with respect to r first. So we need to make sure that our equations are in terms of cylindrical coordinates. So the sphere was x squared plus y squared plus z squared equals 4. That gives you the equation r squared plus z squared equals 4 using cylindrical coordinates. Well, this equation is not solved for r or z. You want to have the surfaces in terms of functions of z and theta. So you'll be r equals, so you need to take the first equation and solve for r. I will give you r equals square root 4 minus z squared. And then the cylinder, x squared plus y squared equals 1 becomes r equals 1. Since we're integrating with respect to r first, we're going to have to find out where does the sphere and the cylinder intersect. So whenever r equals 1, you can substitute this into the equation for the sphere, and you'll have 1 squared plus z squared equals 4, which gives you z squared equals 3, or z equals positive square root of 3. So the sphere and the cylinder will intersect at z equals square root of 3, and whenever r is equal to 1, in the rz plane. Now notice, if the z values are between 0 and square root of 3, that was for r values between 0 and 1, and theta is between 0 and 2 pi. However, if the z values are greater than square root 3, but less than z equals 2, which is where the sphere intersects the z-axis, which was 0, 0, 2, then the r values are only between 0 and the positive square root 4 minus z squared, and theta is between 0 and 2 pi. So again, since the r values are bounded by two different surfaces, above and below, you have to separate this out into two separate triple integrals using cylindrical coordinates. The volume is equal to a triple iterated integral. You have theta on the outside. Theta goes between 0 and 2 pi. The z values go between 0 and square root of 3. That's your middle integral. And then the r values are on the inside. The upper surface was r equals 1, and the lower surface was r equals 0. And then the integrand becomes r after you change the cylindrical coordinates. And then you have a separate solid that you have to integrate over. So plus, now you have another solid where you have theta goes between 0 and 2 pi, plus the integral involving z values are between square root 3 and 2. And then again, r goes between 0 for the lower surface and r equals square root 4 minus z squared for the upper surface. The integrand becomes r again because you're integrating using cylindrical coordinates. Integral from 0 to 2 pi, integral from square root 3 to 2, and then integral from 0 to square root 4 minus z squared for the integrand r, and you integrate with respect to r first, then z, and then theta's last. The sum of these two triple integrals will give you the same value as the triple integral that we found in the last problem, using just one triple integral. So let's try one more problem. We're going to finish this video by illustrating a conversion between rectangular and cylindrical coordinates. So example 7, converting from rectangular to cylindrical coordinates. Convert the following integral from rectangular coordinates to an equivalent integral using cylindrical coordinates. We're not going to evaluate the cylindrical integral afterwards. So the original integral is from negative 1 to 1, that corresponds to y values. The middle integral corresponds to x values. It will be x equals positive square root 1 minus y squared, and the lower limit is x equals 0. The inside integral corresponds to z values. The upper surface is z equals square root x squared plus y squared, and the lower surface is z equals x squared plus y squared. The integrand is x, y, z. We're going to change this triple integral involving rectangular coordinates into an equivalent integral involving cylindrical coordinates. So notice that the y values are on the outside, so the y values are between negative 1 and 1. Your x values correspond to the middle integral, so your x values are between x equals 0 and x equals positive square root 1 minus y squared. And the inside integral corresponds to z values in this case. The z values are between positive square root x squared plus y squared, that's the upper surface, and the lower surface is x squared plus y squared equals z. You need to convert the surfaces to be in terms of functions of r and theta using cylindrical coordinates. So remember, the conversion factors was x equals r times cosine theta, y equals r times sine theta, and then z just stays z. The lower limit of integration, x squared plus y squared, will become r squared using cylindrical coordinates. And then square root x squared plus y squared will become z equals r using cylindrical coordinates. So the upper surface will be z equals r when you convert to cylindrical coordinates, and the lower limit of integration becomes z equals r squared, because we're integrating with respect to z first. It'll be z equals, and then it'll be functions of r and theta for your upper and lower limits of integration. Your integrand, x times y times z, becomes r times cosine theta for x, r times sine theta for y, and then z will just stay z using cylindrical coordinates. But then dz dx dy becomes r dz dr d theta. When you change to cylindrical coordinates, you pick up an extra factor of r multiplied by the entire integrand. Now the outside two integrals, that's describing a region after you project into the xy plane. In this case, the outside integral corresponds to y values, and this middle integral corresponds to x values. So we're projecting to the xy plane, and we have the upper curve, x equals square root 1 minus y squared. That's the right half of a circle of radius 1. And the lower curve is x equals 0. That's the y-axis. The outside integral corresponds to y values. We're integrating between y equals -1 and y equals +1. So we're integrating this entire region in the xy plane in quadrants 1 and 4. So now set up your two outer integrals to become theta on the outside. Theta goes between -pi/2 and +pi/2 for this region. And then r values are between 0 and 1 because this is a circle of radius 1 for the upper curve, and then r equals 0 will become the lower curve. So your triple integral using cylindrical coordinates should be integral on the outside corresponding to theta, -pi/2 to pi/2. Your middle integral corresponds to r values, r equals 0 to r equals 1. Your inside integral corresponds to z values. Its upper limit is z equals r, and lower limit is z equals r squared. Your integrand becomes r times r times r, so you have r cubed, sine theta times cosine theta, and then you also have times z. The value of this triple integral using cylindrical coordinates will be equivalent to the value of this triple integral, which was in rectangular coordinates originally. So this finishes our video on triple integrals in cylindrical coordinates. We talked about how to evaluate a triple integral by changing from rectangular to cylindrical coordinates. If you have any questions about any of the examples in this video, please let me know. Or if you have any questions while you work on the homework for this section, please let me know that as well. And I'll see you in the next video when we talk about triple integrals in spherical coordinates.